Hello and welcome back to the lab. Today on the bench we have an interesting bit of kit that I was asked for a video on. These are Input RC normalizers, and typically when you guys see me use these, I'm doing a calibration on a scope. And I got a question in the comment section that basically said, hey, can you talk a little bit more about these things and explain what they are, how to use them, and why we use them, and what we're doing? So that is this video. So, when doing a scope calibration and alignment, especially in the vertical section, one of the places that a good deal of time is spent is doing these capacitive adjustments on the input attenuators. And that can really make or break the alignment of the vertical section. If these are off, or if the capacitors are off in the front end of this, you can be down on a 475, you could be down 40 megahertz in bandwidth coming through the amplification chain. One of the reasons for that is it's incredibly difficult to build a variable wide bandwidth amplifier. So we have a wide bandwidth amplifier here because we have to go DC to the bandwidth of the scope. But we did a little analog wizardry and we didn't have to make it variable. So we have a front end, but how do we take a measurement? So each one of these ICs is a tech amplifier IC. And so every time the signal goes through it, it gets amplified a little bit. But the total amplification for the channel is fixed. So for the sake of argument, we're going to call this a 10x amplification factor. So whatever comes in on this side gets amplified by a set and very accurate 10x and comes out the other end. Well, if that's the case, how can we make a measurement? Well, we make a measurement by attenuating the front end signal by a known amount. So a large signal comes in, we go through the attenuator, it gets knocked down a known amount, comes in, gets amplified a known amount, gets thrown out and displayed on the scope screen where we have a graticule that's aligned to this amplification chain, and we can make a measurement. That's essentially how the vertical in any non-digital oscilloscope functions. And that's one of the reasons why we also have steps on the front end, because we have set amplification factors. There's a mark right here at 10 millivolts per division where we are not amplifying or attenuating the signal at all. At 5 millivolts per division, we're actually adding a little bit of amplification. At 10 millivolts per division, it's straight through to the back side, bypassing all the attenuators, coming out the back, and then hitting the amplification chain. That's why a lot of the first adjustments are done at the 10 millivolt setting, is because we get the attenuator block out of the way and get it set up so then we can align the attenuator block because we have to use the screen. So it's kind of this order of operations that builds on itself as you're going through the alignment and calibration process. The thing is, on the front side of this scope is we have an input. We have a nominal input, which has a resistive attenuation and a capacitance, or resistive impedance, I should say. Not really an attenuation. The attenuation's in the probe. So we have a 1 megohm input impedance shunted by 20 picofarads of input capacitance. The input capacitance, we want to be as low as we can get it within the ratings due to capacitive reactance at higher frequency signals. As the bandwidth gets ratcheted up, this input capacitance becomes a much bigger deal. This is also true in the probes. In your standard oscilloscope probe, there is a 9 megohm resistor hiding in here, and it's 9 megohm with the 1 megohm input impedance, which ends up with a 10 megohm input impedance when the probe is set to 10x. When it's set to 1x, the 9 megohm resistor is bypassed, and you have the straight 1 megohm and probe capacitance, a little bit more than 20 picofarad, but because of cable and the probe itself. But the bandwidth is significantly reduced. In 1x mode, this probe is only good for like, I think it's 6 megahertz or something like that. Whereas if I kick it to 10x, it's good for the full 100 megahertz bandwidth of this probe. That capacitance is a real problem at high-speed signals. So when we're doing an alignment, what the heck are these things? Well, you'll need a couple depending on what you're aligning, because you will need the RC to match the input capacitance of the plug-in. So this is a 20 picofarad input. I need the 20 picofarad normalizer. I have 20. I have a 47. The 47 was primarily in the 500 series scopes. We have a 22, which I also use quite a bit. Actually, I have several different 7A26s that have 22s. Let's see, my 485 is a 20. 718 is a 20. But we also have this 7A26 right here. Even though it's the same plug-in, it's a 22. So I can't use a 20 on it. So, what are these things? Well, essentially they're dummy probes, but they're dummy probes in a very strange way. They don't have a 9 megohm resistor, so you don't get the full 10x, but you do get to normalize the capacitance of the input of the vertical that's being aligned. So instead of having a probe hooked up, all this wire, all this other stuff, you can plug the signal directly into the back of here, usually with attenuators, because it's coming out of a 106, which is a pretty high amplitude square wave. And it gets knocked down. And then sometimes you'll even have a 50 megohm, or a 50 ohm, not 50 megohm, 50 ohm terminator on the front of this, depending on what you're doing. There are a couple of adjustments that need 50 ohm. Now, if you're doing a 400 series scope, or you're doing something that you'd like better than 50 ohm, or that you're going to primarily use in a 50 ohm system, what you can do is you can do the alignment not with a normalizer, but with a 50 ohm terminator. When you do that, you just have to know that you've skewed the alignment, not in a bad way, but towards 50 ohm as opposed to what would be a nominal input capacitance. This is so important because of probes. The probe has to faithfully pass the signal at the probe tip. Everyone's familiar with the compensation capacitor at the probe, and even these have a compensation capacitor in them. So, essentially, dummy probe. There's two ways to really use them. One way Tech does not recommend, which is set this to 20 picofarad and then align all the plugins to that. And if you do that in a really tight tolerance and tight standard, you can prevent having to tweak this capacitor every time you hook up a new probe to a scope. For the most part, everybody kind of got into the habit of tweaking the capacitor every time checking the scope with the internal calibrator, tweaking the capacitor to make the square wave look right, and so they match the scope to the input. Now, when you do it this way, because these inputs are not exactly at 20 picofarads, this could be at 21, this could be at 19, when you move the scope down, you'll have to recompensate the scope for the input. So every time you hook a scope probe up to a scope, compensating it for the inputs, usually a good idea. And in some labs, they may have had a normalization program that they checked all the scopes and no one wanted to touch the probes and do all that. In the 400 series, they're stamped with a nominal capacitance, but if you actually measure the capacitance of the front end of the output, it's going to vary a little bit. When they were released from the factory, the input capacitors were set in such a way that if you compensated a probe on channel 1, that same probe would compensate on channel 2. Wouldn't be exact, but you could get it to compensate so you could mix and match the probes. If those get too far out of balance, you may not have that compensation correct. And so that's one of the reasons why when I'm doing an alignment, unless I absolutely have to, I don't mind tweaking the probe, and I use these so I can tweak these instead of the probe. And that way, I can preserve what tech rolled them off the factory with, assuming they haven't been screwdrivered in the past. If they have, start with a nominal middle ground and then work from there. But you definitely want to get the channels at least in the same scope. From scope to scope, it's not that big a deal, but internal in the same scope, you want to be able to use the same probe set. You don't want to have a 15 picofarad probe for channel 1 and a 22 picofarad probe for channel 2. Gets a little weird. So, what is in one of these things? Well, it's a really, really simple circuit. We have the input side, which would be over here. We have a 1 megohm half-watt resistor. We have a fixed capacitance, and then we have a variable capacitance, and then we have the output. And that's it. So, essentially, this one's probably a 20... Yeah, I'd say this one's a 20 picofarad because it's got a 2 to 8 and then an 18 fixed. Was I right about that? Yes, I was. 067 053800, 067 053800. So this is exactly what's in the 20. The only difference between the 22 and the 47 is this shunt capacitance is probably a little bit big. Is going to be bigger. Not probably, it is. So typically, I'm not too hung up on the exact capacitance of the normalizer. So what I'll typically do is, if I know channel 1 in a scope alignment isn't too far off, I'll set the capacitor for channel 1, and then I will adjust all the other channels to get close to channel 1, other than a 400 series. In a 400 series, I will adjust the shunting capacitor, or the adjustable capacitor for each channel before I do the channel. But once you set it, it's fixed. You can't adjust it during the alignment, or you'll have attenuator sections that don't match. Because once we set the capacitance at the front end, we want to normalize this capacitance so it's all the same. Because if you don't, you'll have to reset the probe every time you change ranges, and that's what we don't want to do. So once it's set up and the square waves are flat off, all of these attenuators match that input capacitance. So that way, once you set the probe once, and also any range you set the probe in, it's good for the whole channel, not necessarily, so you don't have to, every time you change ranges on the front, you would have to readjust if these were out of whack. And they can get really far out of whack. These 8 capacitors specifically have a huge effect on the displayed signal on the scope. Now, the documentation for this does go in and state that these can be used as a dummy probe, even though they don't have the full 10 megohm. It's any high impedance probe. So essentially, once the front end is normalized for the capacitance, then it's good for a 10x, a 100x, a 20x. Doesn't matter what the probe is, it's going to be set up correctly, and it's going to show, and it's not going to skew the bandwidth due to probing capacitance. So we have a 1 kilohertz square wave coming in from my 106. Turn the readout on so you guys can see. Don't mind the noise that shows up in the camera every once in a while. That's the readout. But we're at 2 volts per division, and everything looks good. This is a nice square wave that would typically show up on this scope. If I adjust the tuning capacitor down in the bottom, well, don't short it out, but adjust it, we can see the compensation goes up, and then we can overdamp it. So this is underdamped, overcompensated, undercompensated, and then we can make it just right. So now that would be set up for doing the alignment. So it looks good. If we were setting this up to do an alignment, it would be on the 10 millivolt range. But this is now ready to align the rest of the attenuator section. If you were doing the in-house alignment and you were setting up the scope to be used primarily in a 50 ohm system where you were doing some high frequency things like that, instead of using the RC normalizer, we would put a 50 ohm terminator on the front of the scope. This isn't a bad thing by any chance. This is just biasing the alignment of the scope for a 50 ohm system versus a high impedance measurement system. If it is set up for 50 ohms, sometimes some probes will not compensate because the input capacitance will be a little too far off. So, but that's typically okay because when they're set up for 50 ohm systems, they're used with inline serial terminators. So one of the reasons that this is called a normalizer and not a standard or a reference or anything like that is because it was never intended for this to be a capacitance standard. This is just a check step, so that's why they went with normalizer to eliminate some of the confusion. So I hope that eliminates some of the confusion on how and when to use RC normalizers in the course of a scope calibration. This video came from some viewers' questions and comments, so as always, I read all the comments in between all the videos, and I look forward to talking with everybody down below. Patreons are running a little bit further ahead than YouTube. Videos are up on Patreon first for a little while, then they make it to YouTube. At the time of this recording, there was nothing behind the paywall, and at the time of this recording, there still is nothing behind the paywall for Patreon, but their assistance helps keep the lights on in the channel and the video coming. So without them, a lot of this wouldn't be here, and without you guys, this wouldn't all exist. So if you have any questions, comments, or concerns, hit me up in the comments section below. As always, more is on the way, and I will see everybody in the next video.